Okay, we're back. All right, this is part three of our lecture. We were just talking about the idea that in this review, we want to make sure we understand the Earth's radiation budget. We're keeping track of where heat comes from and where it goes in the Earth's atmosphere. I mean, we got basically two sides of a little graph right here. We were going to make a little model, little conceptual model over here on the left-hand side about how shortwave radiation from the sun is mostly transmitted through the atmosphere and eventually some of it makes it to the ground. We call that downwelling shortwave radiation or shortwave down. And then some of that will be reflected and that will become shortwave up, radiation that was reflected by the Earth's surface and is now, I mean, this radiation comes from the sun. It's just shortwave, it's just radiation that got reflected up. And the difference between the shortwave down and the shortwave up is how much radiation the ground absorbed from the sun. Now, this is a complicated business as to how much of that shortwave radiation will get absorbed. It has to do with length of sunlight and sun angle and so on. We'll talk more about that later. But at night, the story is, well, actually, both. I drew it as night there, but actually, this would happen both during the day and the night. The ground is also emitting radiation. Long wave radiation or heat is being emitted upwards. This is long wave up or upwelling long wave radiation. And some of this is going to go right up to space, but some of it is going to get absorbed by clouds and by greenhouse gases in the Earth's atmosphere, like carbon dioxide or water vapor, and then get emitted back down to the surface. This idea that was somewhat complex in here about the atmospheric window, that did not make it to the final version of the test. Let's not worry about that. But in general, this long wave radiation doesn't make it to space. It gets absorbed by the clouds and the greenhouse gases in the atmosphere and does not make it all the way to space. Some of that actually gets emitted back down toward the surface of the Earth. It can be measured as long wave or terrestrial radiation coming down from the sky towards the ground. That's called downwelling long wave radiation or long wave down. So this is how we get to that business of the greenhouse effect, because we are adding, by burning of fossil fuels, carbon dioxide and other greenhouse gases into the Earth's atmosphere that increase the amount of long wave radiation being emitted downward, which keeps the surface of the Earth warmer than you would expect. This rest of this business of how we fully balance the radiation budget is a little bit too technical for what we were doing in the class and what was able to make it to the test. So we have this idea that we had a radiation budget, but it kind of becomes interesting how the role of clouds is complicated. How during the day, clouds largely work to help keep the Earth cool by reflecting sunlight away. Clouds have a very high albedo. On the other hand, both during the day and during the night, clouds are part of the greenhouse effect. They are absorbing long wave radiation or terrestrial radiation and keeping it from getting out into space and then emitting it back down towards the surface of the Earth. All right, so we seem to have made it through the first part of that heat lecture. So let me just click you over here to the second part. And the good news is some of this here we will be able to keep a little bit shorter. I think that this one gets a little more cut short than some of the other ones do. I mean, really the central issue of the second part of it is what's determining the amount of long wave and short wave radiation that comes down from the sky to the surface of the Earth. Well, shortwave radiation, the radiation from the sun that is warming the Earth up, is basically determined by how high in the sky the sun is and the length of daylight. Now, in this lecture, we went to a pretty good amount of trickiness to figure out about like noon sun angle and stuff like that. But I think in the end, in the interest of keeping this test a little bit shorter, we can throw that stuff out. We're not going to actually compute any of the noon sun angles or anything like that on the test. Hey, by the way, though, you do need to know that the Earth's orbit is this big ellipse that is closest to the sun on January 4th, and it is actually a little bit farther from the sun on July the 4th. So yeah, we are actually a little closer to the sun in January than we are in July. Don't get me wrong, it's not a huge difference. It's exaggerated on this graph right here. But we are actually slightly closer to the sun. Why is it cold in the winter? Well, that's just because we're in the northern hemisphere that's tipped away from the sun at that time. All right, all this stuff about like beam spreading and stuff like that, in the interest of keeping the test a little bit smaller, especially with our snow days and stuff like that, I'm going to go ahead and throw out this business of like the annual cycle and about like these different length of daylight calculations and so on. This kind of stuff is not going to be on the test, okay? You had questions about it on your exit tickets. You had things about it on your homework. You have proved enough to me about that. So we won't actually be doing any of these kind of calculations or estimations. All right. Same sort of thing here. We got these estimates over here about the different times a year and so on. Let's go ahead and pop through this stuff real quick here and find where we get back on track. As much as I like this stuff about solar declination, again, that is the latitude on the Earth where the sun is directly overhead on a given day. Again, the test was already pretty big, so I went ahead and said solar declination is not on the test, which means you don't need to know how to use an analemma. You don't need to be able to compute the solar declination and any of those kind of problems there. And that also means you won't be able to do the stuff you're doing here, starting on slide 57 about noon sun angle. Okay. Again, the things you did on exit tickets, the questions you answered along the way, as far as I'm concerned, we have met our obligations on that. So we're going to keep that simpler this semester and not actually get bogged down in any of these things. Although in the future, I think we will do more when different students take this class. All right. So we kind of were able to cut down this stuff about shortwave coming down from the sky into just a few basic ideas about like the times of the year and stuff like that. Now, as to what determines the amount of long wave radiation coming down from the sky, this is going to be about greenhouse gases. How the greenhouse gases, in particular carbon dioxide and water vapor, help maintain the Earth's temperature by absorbing long wave radiation that the Earth emitted and returning it back to the surface of the Earth. And this is a necessary thing. If this wasn't happening, the Earth would be much too cold to support life. But by adding too many greenhouse gases, of course, we are effectively we're putting too warm of a blanket on the surface of the Earth, and we are not letting enough heat out into space and instead absorbing it and re-emitting it back towards us. We now know that by adding greenhouse gases to the atmosphere, they are enhancing the greenhouse effect and warming it. We know this is true. We can have observations that show things like how the Earth is warmer than usual and how this trend has been going on really since the beginning of the industrial age. We know from measurements things like the sea ice is melting. And while strictly speaking, like from the point of view of like hypothesis testing, this is not strictly speaking proof. I mean, there could be natural processes that are canceling out what humans do, but this is really quite a smoking gun. Based on the known physics of the Earth's atmosphere, it would be very difficult for us to be wrong about this, okay? It would take an amazing string of coincidences for us to not know correctly how that this is not working. It's very strange that our prediction as to how much the planet should be warming is almost exactly the amount the planet is warming. And that is about as good as we're going to be able to understand what we're doing with the greenhouse effect for the purposes of this class. Now, in there, we also talked about that lecture about the Kyoto Protocol, an attempt to build some kind of framework, which has largely been surpassed now by the Paris Agreement of 2015, I think it was. But these were all ways to find new market-based solutions to sort out how to improve how to get a handle on the emissions of greenhouse gases. And this is all really interesting and how it was supposed to work and so on. But realistically, again, the questions it was just getting too much detail. I'd rather focus on the stuff that's specifically about the physics of the Earth rather than policy issues. I would love to talk to you guys about this at length if anybody wants to discuss it at a lab or something someday. Anyway, we didn't end up signing the Kyoto Protocol, and now we're ending up pulling out of the Paris Agreement. So all these things are kind of falling apart around us, which is not terribly surprising. The Paris Agreement of November 15 is the current set of standards that the president is currently pulling us out of, that was trying to limit global warming to only 2 degrees Celsius, but that won't be able to happen without us being part of it. And we don't, again, the words Paris Agreement don't appear on the test or whatever. All right, so I think I'm at a good stopping point. I think this tool is about to stop me because I think we're right around 10 minutes. All right, I will move on part 4 of this review to start walking you through some of the other lectures.